right, grade 11s, we're coming to the moment of a force. You listen carefully. Now, what is moment of a force? Okay? Moment of a force is called the torque. It is the force that has a turning effect, or is the turning effect of a force. Let me put it that way. Turning effect of a force, moment. And we call that turning effect of a force torque. All right? Now, torque is the product of distance between the pivot and the perpendicular component of the force on the object. Now, we're talking, like I wrote earlier on, I said turning effect. So something is turning here. Now, if something is turning, there should be a point at which it is turning. We call it the fulcrum, or what we call the pivot. Okay? So we are told that this torque here, which is that shown by that symbol there, equals what we call the perpendicular, the perpendicular component of the force on the object times the distance, okay, d, from the fulcrum or the pivot, okay? And when we do that, we will be able to know how much torque is acting on that particular object when a particular force is applied at a particular distance. Okay? Now, an object will experience torque if a force acting perpendicularly causes the object to rotate. Obviously, when it rotates, it can rotate in a clockwise direction or in an anti-clockwise direction. Okay? Let's look at this example here. A mass of 600 kilograms is lifted off the ground by a crane. Calculate the torque if the mass is placed at a distance 20 meters from the pivot. Okay, so torque, this funny T is torque, it's F times D. So that will be equal to the force applied on this crane, on this mass here, for it to be able to be lifted upwards. Maybe let me just put the mass here. 600 kilograms is to be lifted upwards by a crane. So the crane connects there and pulls it upwards, so it goes up. Okay? Now, when that happens, the force that is to be overcome for this thing to go up, and then this is the turning point. This is the fulcrum, pivot. Okay? For this mass to go up, should be equal to the weight of the object, the force of gravity which is given by mass times gravitational acceleration. So it will mean that this force here is m times g, then times d there. So this will be equal to 600 times 9.8, which is the F, the force, then times the distance we are told is 20 meters from the pivot. So that times 20. Let's see what that will work out to. 600 times 9.8. 600 times 9.8 times 20. Okay, that works out to 117,600. What is the unit here? This is Newton, the force. This is distance, meters. So Newton meter. Okay, so that then becomes the unit of measurement for torque or for moment of a force. All right. One thing we also need to know is that when the sum of the turning moments or the torques around a rotational axis is zero, we have what we call a state of equilibrium. Okay, a state of dynamic equilibrium. Let's look at this example to understand this. Tembi of mass 50 kilograms and Musa of mass 70 kilograms are sitting on either sides of a seesaw. Okay, so some seesaw there, Thembi, Musa. Okay? Musa is sitting at a point, they want to keep the seesaw balanced, so they don't want to be moving up and down, balanced. Musa is sitting at a point 2 meters from the pivot. So Musa, 2 meters there. And then where should Thembi sit so that the seesaw could be balanced? Okay? So what we know we need to understand here is that the sum of the torque, maybe let's say left here, should be equal to the sum of the torques right. Okay? So to do that, we'll say, okay, for left, let's look at Musa, which is 2 meters away. So the torque for Musa, it will be force acting on Musa times the distance for Musa equal the force acting on Thembi times the distance for Thembi. So this is Musa. This would then be, again, this is force of gravity because we're looking at their weights actually. So for Musa, we've got 70 kilograms. So that will be 70 times 9.8 times 2 should be equal to 50 for, sorry, here, this should be 50 for Musa, and then Thembi, it's 70, sorry. So 70 times 9.8 times the distance. We want to know how far Thembi is. And from there, you can calculate for the distance of how far Thembi should sit on that seesaw so that they have a balanced seesaw, not moving. See you in the next section.